And now we're going to tie together orbitals with the periodic table. This is, okay, I keep saying this is my favorite. Okay, everything's my favorite, fine. But this whole idea that we have electrons that are in orbitals and that the orbitals are shaped in a certain way, and these electrons in these orbitals, they also have energies that differ from each other in predictable ways. And I want to draw up here, it's a type of mnemonic device. I don't know if mnemonic's the right word for it, but it's one method some people use to remember which orbitals are lower in energy versus other orbitals. But I want to challenge this technique I'm going to show you in a second with just using the periodic table. So let's do that. All right. How was everyone? Did you have a good break? Okay. So here we go. Orbitals. We just saw that if we're going to be talking about an electron in a specific orbital, we give the principal quantum number, and then we give what type of orbital it is. And so if we look at the lowest energy possible orbital there is, it's a 1s orbital. That's where principal quantum number, n equals 1, and L equals 0. All right. So in terms of, again, thinking about the Bohr model of the atom and other ideas like that, that's going to be the lowest energy orbital. So I'm going to draw this at the bottom. If we think about this in terms of high energy being up here, lower energy down here, 1s orbital is there. Okay, there are no other possible orbitals that exist where n equals 1 because of what we just talked about with the rules of quantum mechanics, and that L can only equal 0 when n equals 1. So there's 1s orbitals and that's it. There's no 1p orbitals or 1d orbitals or anything like that because of that rule. All right, so that means that the next possible orbital that there is the 2s orbital. So we're going to put that is higher in energy than the 1s orbital. I'm going to move this ever so slightly, my camera over. Okay. So 2s orbital, a little bit higher in energy than the 1s. Are there 2p orbitals that exist? That would be n equals 2, and if L equals 1, giving a p orbital. Yes, those do exist, again, based on those rules of quantum mechanics. So there are 2 p orbitals. So energy-wise, they're going to be, at least for hydrogen, they're going to be on the same level, so I'll just draw them like that. And then we're done. There's no 2d orbitals for those reasons we mentioned before. And so this pattern follows. Now that we have principal quantum number 3, we now are allowed to have L equals 2, which is a d orbital. And then when we get to 4, we have all 4 of them. S orbitals, p, d, and f are now all allowed. 4s, 4p, 4d, and 4f. And if we continue on from here, we're just going to stop at f orbitals, again, because g orbitals are not seen in practice. Okay? So 4s. Now we have 5s, so I'll fill this out. 5p, 5d, 5f, 6s, 6p, 6d, 6f. And I think I will stop there. Okay. So there is a trick you can use. It's sometimes called the diagonal rule, where once you have drawn all these orbitals up like this, you can now draw diagonal lines in this way. You start down at the bottom, and you draw it going up like that, and diagonal, diagonal, diagonal. And you might be wondering, why the heck do I want to do this? And I'll tell you why. Okay, it goes on from that. Is that this is the order of the energy of orbitals that exist in the universe. This is the orbital energy order for any atom that isn't hydrogen, just a hydrogen atom by itself. Okay, hydrogen atom floating around by itself, pretty rare in nature. You can see them up cosmic rays and in labs and things like that. But for all intents and purposes, for everyday life, following this order is telling us the energy of those electrons in all the possible orbitals. So this, let's see what this would tell us. So that means that a 1s orbital, lowest energy, followed by 2s, followed by 2p, followed by 3s, followed by 3p. So there's nothing too wild or unexpected happening yet. But look at this. The energy of a 3p orbital is followed by 4s, and then we go back to 3d, and so now we're out of order, and then to 4p, then 5s, so 5 inserts itself, and then we go back and there's 4 again. Okay, so you can see that there's this mashing up of order that's seemingly really hard to predict. And so that is why it is taught to write out this order in this way and then draw these diagonal lines, and then you are able to compare different orbital energies to each other. Okay, why would you want to do this? What is an example of why you would even ever want to do this? Okay, this is if you're trying to figure out, given an element, where are the electrons? How many electrons are there, and where are they? In what orbitals are they? So let's use carbon, for example. Okay, so looking at a carbon atom, where are those electrons? Okay, so carbon, how many electrons does carbon have? Okay, if you're like, off the top of my head, I don't know. So you could just always grab your handy dandy periodic table and take a gander and find carbon. And then you would say, all right, carbon, element 6. So there are 6 protons. If it's a neutral, there are 6 electrons. All right, so we could start out there. And we say, all right, carbon, 6 electrons. And now you're trying to designate where the heck are those electrons? Okay, well, electrons are always going to start out and will exist in the lowest energy orbitals that are available. They're not going to be hanging out at high energy orbitals. All of nature will spontaneously go towards the lowest possible energy configuration. And that's what electrons do naturally. They will fall down into the lower level orbitals. So that means that we will have 2 electrons in a 1s orbital. Each orbital is allowed to hold 2 electrons. So this 1s orbital, we could designate that. How well is this purple coming? That's pretty good. Okay, so the 1s orbital is allowed to have 2 electrons in it, and so we can designate that with a superscript. Okay, so that takes care of 2 of the electrons, but there are 6 total. So what's next? We look here, there's a 2s orbital is the next highest in energy. And so we can write that here, 2s. And then once again, in this 2s orbital, 2 electrons are allowed. And so we put them in there. And now the 2s orbital is full. And we go to the next highest energy. Okay, so after the 2s, now we go to the 2p. And we can put in the 2 remaining electrons in carbon into the p orbitals. All right, so this is what we call electron configuration. All right, electron configuration telling us where those electrons are. We are also going to be drawing out the orbital energy diagrams, but I want to show this because I want to now tie this in with the periodic table and show you what is happening. Okay, so I want to make sure that this, at least the important parts, which is essentially up here, that we can see it. Okay, so when we think about carbon and that it has these 6 electrons, we can essentially start with hydrogen and do kind of a counting, and we can see where are those electrons, and knowing that hydrogen has 1 electron and that the 1s orbital is lowest in energy, and so that means that the hydrogen, that 1 electron is in a 1s orbital. And then we have helium. Helium now has 2 electrons, neutral helium. We're going to just be talking about neutral atoms here. It's got 2, and so that second electron will go in the 1s orbital. And then we can come over here to lithium. Lithium, 1s orbital's full, so now we're in the 2. We are now filling the 2s orbital here. And then we look at beryllium. And we still have 1 more space in the 2s orbital, and then that gets filled. And then we come to boron. The 1s is filled, the 2s is filled. Now we are beginning to fill the p orbitals, those 2 p orbitals. Now notice here how there are 6 elements across. How many p orbitals are there? How many different configurations of p orbitals are there, different orientations? We saw that there are 3 at m sub l minus 1, 0, plus 1. That was one of my questions for Lansamillion that you answered, right? So there are 3 different orientations. There are 3 different p orbitals. And each p orbital can hold 2 electrons. 2, 2, 2. That's a total of 6. 1, 2, 3, 4, 5, 6. Not a coincidence. Okay, so right here, all these elements are filling the 2 p orbitals. These elements are filling the 1s orbital. These are filling the 2s orbital. These are filling the 3s, 4s, 5s, 6s, 7s. So we call these 2, and to really, I would say formally, helium should be over here, but it's just moved over there because it's so inert and it acts like a noble gas. I mean, it is a noble gas, so that's why it's over there. But in what we're talking about, all of these elements, their last electrons to be added are all being put into the s orbitals. So this here is called the s block, because those last electrons to be added are in the s orbitals. Over here, all these elements that are here, that are in this block, that's showing that's 6 across, because we have 3 p orbitals, 2 electrons each, 6. All these are filling the 2p in this row, or in this period, I should say. In this period, we're filling the 3s. I just said s. Let me start over. These are filling the 2p orbitals, the 3p, the 4p, the 5p, the 6p. Okay? So the periodic table is lining up with what is being filled first. What's being filled first? It's always the lowest energy orbital. Okay. Let me add one more thing in here, because we were just looking at carbon was our example. And so far, we've only talked about the 2s and the 2p in terms of tying it in with the periodic table. What about the 3d orbitals? So remember, there aren't 1d orbitals. Those don't exist. 2d orbitals don't exist. 3d is the first orbital that can exist that is a d orbital. It's got to be 3d. Okay, following all of our rules of quantum numbers. And those start getting filled right here. So scandium, always next to calcium, because after calcium exists with its 20 protons and its 20 electrons, and they've just filled the 4s orbitals, then comes the element scandium. And scandium is where we now put an electron for the first time into a d orbital, into that 3d orbital. So we've seen 1s, 2s, 3s, 4s. We see on the periodic table the 4s orbital is filled first, followed by 3d. It shows, it's right here on the periodic table. It shows us. We don't need to draw out all this mumbo jumbo and going like, oh, 4s is filled before 3d. Oh, I better memorize that. No, you just need a periodic table. It's all there for you. Isn't that amazing? I love you, periodic table. All right, 4s, 3d. Okay, let's look at the 3d period right across here. How many are there? I'm going to block it so you can't count. Okay, how many should there be? How many d orbitals were there? D orbitals, L equals 2. So what can M sub L equal? M sub L gives you the orientation. And if L equals 2, then M sub L can equal -2, -1, 0, +1, +2. How many is that? 5. There are 5 d orbitals. So how many electrons can fill those 5 d orbitals? 2, 4, 6, 8, 10. Yes. Okay, there are 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, that is where that comes from. So we have just filled that. Remember, 1s, 2s, 3s, 4s, and then 3d. And then what's this? When we get to gallium, what orbital are we filling? 2p, 3p, 4p. So we went from 4s, 3d, to 4p, but again, it's all here on the periodic table. We didn't need to do that thing. Okay, and then we go back to here. Now, and we would follow the rules. Now, when you get to lanthanum, you might be like, oh no, now what do I do? There's this double asterisk. What's happening? All right. This is where we have to jump from here and then go down to here. Double asterisk, double asterisks. And the only reason why this isn't just inserted into the periodic table is because we are a society that lives with either, depending on where you live, 8.5 by 11 inch sheets of paper that are either vertical or horizontal for a periodic table, or there's the A4 size that's used in European countries and other countries. Okay, so we're essentially, we confine ourselves to these certain shapes, not these really long banners. Now, if you wanted to include the F orbital elements here, these lanthanides and actinides, and insert them into here, you would end up with a periodic table that was just really long. It's not a big deal. It's not a problem. It would just be really inconvenient for textbooks and for posters like this, etc. So that's the reason why we have everyone jump from and use little asterisks, go, hey, go down there. Element 57, element 58, 59. And so as long as we're just paying attention when we get down into that realm, then once again, we can see what is the orbital energy of filling. Where are those electrons going to go? Okay.